Hello, my name is Jaden Lindquist, and today I'll be teaching about the relativistic addition of velocities. Before we start to talk about relativistic addition of velocities, let's review briefly classical velocity addition, which I believe we learned about in Physics 105. So for both classical and relativistic velocity addition, there's 2 points to remember and to know. First is that velocities add, like regular numbers, in a one-dimensional motion. And it's important to note that we restrict our consideration to one dimension just for simplicity's sake. Suppose, for example, that a baby is traveling in a stroller. She throws her toy forward. What is the speed of the toy to an observer? And also, if the baby were to throw her toy backward, now what is the speed of the toy relative to the observer? The equation we use to solve this problem is by adding velocities classically, and it's u equals v plus u apostrophe. U here would equal the velocity of the toy relative to the whole Earth. V is the velocity of the stroller, and u apostrophe is the velocity of the toy relative to the stroller. Here we would use a plus or a minus sign in one dimension, and for example, in this situation, positive would be forward or to the right, and negative would be backward or to the left. So, when the baby throws the toy forward, v will be equal to 1 meter per second, and u apostrophe would be equal to 1.5 meters per second. The addition of these velocities classically, or u, is 2.5 meters per second, which is the velocity that the observer will observe the toy at. And this is going to be a faster velocity because the velocities are added classically. When the baby throws the toy backward, u will be equal to 1 meter per second minus 1.5 meters per second to equal negative 0.5 meters per second, which is its added velocity. The negative sign here in the answer of negative 0.5 meters per second means that to the earthbound observer, the toy moves backward. So this is how classic velocity addition works. This leads us to the true topic of our lesson, which is relativistic velocity addition. This second postulate of relativity varies from the classic addition of velocity that we've just been studying by stating that classical velocity addition does not apply to light. And that is what we'll be exploring in this example. So, imagine a baby with a flashlight strapped to her chest, traveling at night along a straight road toward an observer. If classical velocity addition applied to light, then the light from the baby's flashlight would approach the observer at a speed of u equals v plus c, the same equation we used before with c being substituted for u apostrophe, c being the speed of light. But we know from experience that light will move away from the baby, which is moving, at speed c relative to the baby, and light will move toward the observer at speed c too. So this is kind of a conundrum because either light is an exception or the classical velocity addition formula only works at low velocities. The correct formula for one-dimension relativistic velocity addition, it takes into account the speed of light, and it is u equals v plus u apostrophe over 1 plus vu apostrophe over c squared, where v is equal to the relative velocity addition between two observers, u is the velocity of an object relative to one observer, and u apostrophe is the velocity relative to the other observer. Note that the term vu apostrophe over c squared becomes very small at low velocities, and this formula gives a result very close to classical velocity addition in that case. Keep in mind that velocities cannot add to greater than the speed of light, provided that v is less than c, and u apostrophe does not exceed c. As before, we see that classical velocity addition is an excellent approximation to the correct formula for small velocities. So, as a practice problem, suppose a spaceship is approaching the Earth at half the speed of light and shoots a canister at a speed of 0.75 times the speed of light. At what velocity will an earthbound observer see the canister if it is shot directly towards the Earth? Because the canister and the spaceship are moving at relativistic speeds, we must determine the speed of the canister by an earthbound observer using the relativistic velocity addition instead of simple velocity addition. So we'd employ the exact same equation that we've just gone over, which is u equals v plus u prime over 1 plus vu prime over c squared. And now if we plug in our variables, velocity of the moving object is 0.5 c, the velocity of the shot object is 0.75 c. If we plug those into the equation, simplify, then we'll get 1.25 c over 1.375 c, which is equal to 0.909 c. And that concludes the lesson. Thank you so much for watching.